Okay, you may or may not have noticed that up until now, all of the conservation of mechanical energy questions that we've done have not had springs in them. So it's time to introduce springs. Now, to do that, we need to first do a little bit of background because we need to talk about something that's called simple harmonic motion. And maybe, depending on who you had for first semester grade 12 math, you maybe have already heard of this. But we're going to do it, me assuming that no one has. Okay, so first we need to talk about what I do know you've heard of, and that is periodic motion. And I know you've heard of this because we did it in grade 11 physics. Periodic motion, and we would have talked about it when we were doing waves. Periodic motion is simply motion that repeats itself. Motion that repeats itself precisely, exactly, precisely over a given period or amount of time. Given period of time. So, for example, the Earth revolving around the Sun, the Earth rotating on its axis, the Moon revolving around the Earth. All of those things are periodic motion. They repeat their cycle exactly over a given period of time. Now, if this periodic motion is generated by a linear restoring force, if created, if caused by a linear restoring force, and I'll explain what a linear restoring force is in a minute. Linear restoring, it really is an S, force, then the results in simple harmonic motion. Okay, so if the motion that's repeating itself precisely over a given period of time is created by something that we call a linear restoring force, then you get simple harmonic motion, and physicists like to say marker ink, so we often abbreviate it SHM. Now, what's this linear restoring force? Think back to when we did springs in grade 11, and we talked about the fact that, okay, we have this spring here, and we're going to put a force on it to stretch it. But the more I stretch it some distance x, the bigger the force is. And if we were to plot it, we would see with x here and f here, we would see that it was linear. The more when the x is tiny, you don't need a lot of force to stretch it. But the more you stretch it, and the same is true for compressing it, the bigger the force gets. So it's linear. That's where the linear comes from. The restoring part comes because if I stretch this spring out, the spring isn't going to like it. And the spring's going to do everything it can to get itself back into its regular shape, to get itself back in, to restore itself. And so that's what we mean by a linear restoring force. And if you remember, Hooke's law was F equals kx. So the bigger the spring constant, the more heavy duty the spring, remember the spring constant was about how thick or how light the spring was. So the bigger the spring constant, the K, the more force you're going to need to stretch it some distance x. Okay? So now, what this is saying then is, if periodic motion is caused by this type of force, then that periodic motion is going to be simple harmonic. So all simple harmonic motion is periodic, but not all periodic motion is simple harmonic. Simple harmonic is like a subcategory of periodic. Just like all bananas are fruit, but not all fruit are bananas. So bananas and simple harmonic motion are subcategories of fruit and periodic motion. Now, perhaps to understand this whole linear restoring force and repeating itself precisely, we need to think about a system. So imagine I have a spring hooked to a wall, and on the end of the spring is a box. And the spring isn't stretched right now, and the box is happy. They're both just sitting at a position that we would call the equilibrium or the rest position, where x is equal to 0, because it's not stretched. But I like to not necessarily leave things as they are, so I'm going to take the box with the spring attached, and I'm going to stretch it out here some distance. X is equal to A. And when I do that, now the spring isn't happy. The spring wants to try to restore itself. It wants to try to pull itself back. Now at the moment I'm holding it, so the velocity at this spot is 0. But as soon as I release it, it's going to begin to move. And it's going to begin to move because when I'm holding it out here, it has elastic potential energy. And if you remember, elastic potential energy is energy that is stored in something that's stretched or compressed, and when you release it, it's going to cause the object to move. So if we were to listen in on what's going on with this spring, we would hear the spring being very unhappy. The spring would be like, man, I hate being stretched out this way. This is like mega uncomfortable and like I don't like it at all. And because it doesn't like it at all, it's going to say, come on, everyone, we need to work together and we need to pull this box back into the rest position. And so all the little molecules in the spring begin to exert a force on the box, moving the box this way. Of course, it's an unbalanced force because there's no friction. Our surface is frictionless. And so the box picks up speed, and it gets closer and closer to the rest position. Okay, almost there. Okay, stop. So when it gets to the rest position, the spring stops pulling because now it's at the rest position, the spring's happy. But the box has been picking up speed all the way along, and so it's an object in motion that's going to stay in motion. So even though the spring has stopped pulling it, the box is going to keep moving. Oh no, this isn't good. Okay, everyone, quick, we need to push. We need to push on this box to try to prevent it from squishing us any further. And so the box slows down, till some point in here, x is equal to negative A. The spring brings the box to rest. Phew! Finally, we got it stopped. But oh wait, this isn't good because now we're all scrunched into this tiny little place and like this is really uncomfortable and hot and stinky and everything. Okay, everyone, we need to push the box back out. And so the spring now pushes the box back out. And it's an unbalanced force acting on the box. So the box picks up speed. It gets closer and closer to the rest position. Almost there, just a little bit more. Okay, stop. And the spring stops pushing. But the box now has a speed, and so the box doesn't stop. It keeps moving. With this, an object in motion is going to stay in motion with a velocity past the rest position. Oh no, not this again. Okay, everyone, we need to pull it back. And so now the spring begins to put a force on the box to try to prevent it from stretching it anymore. It eventually brings the box to rest. Oh, okay, we got it stopped. Okay, now we need to pull it in. And it starts to pull it in again. Almost there. Okay, stop. But the box keeps going. Oh, no. And this would go on forever. So this is what's called simple harmonic motion. At this point in the middle, the speed is going to be the maximum because it's the spot where it's speeding up. The force stops. So at this point, it stops speeding up. But it's right before it starts to slow down. So at this spot, its speed is maximum. Now, simple harmonic motion is special because it is what we call sinusoidal. And again, I think from first semester grade 11 math, you would have heard this term. To understand it, imagine that I attach a pin to the box. And so as the box oscillates, it's going to be a line going back and forth. But now if I was an octopus, I would take my paper and I would move it up as the box oscillated. And so I'm going to slide the paper up and the box is oscillating with the spring attached. And so what we would end up getting would look like this. And if you draw a line down the center, You would and turn your head sideways. You would see this is a sign